Okay, class, today we're going to talk about ionic compounds and how to form them. This is located in Chapter 2 in your book, so hopefully you printed the notes and are keeping up. In the previous video, I told you about how to form ions and what ions are, being an atom with a different amount of electrons. Okay, anions and cations, for instance. So, first we're going to talk about formulas for ionic compounds. So a chemical formula is a concise list of the elements in a compound and the ratios of those elements. So NaCl is table salt, KBr is also a type of salt. Lithium hydroxide, LiOH, is also a type of ionic compound. And sometimes you'll hear me use the term salt and ionic compound interchangeably, at least as it pertains to this course. A formula unit is a set of oppositely charged ions that compose an ionic compound. You may recall that a molecule refers to compounds with a covalent bond, which we'll get into next chapter. So you may say that what I have shown is water molecules, not water compounds. Or they are compounds, but they're not formula units. But if you had the same thing but ionic compounds, you would say that those are 3 formula units. Okay, all of those are compounds. I apologize for misspeaking a second ago. They're all compounds. It's just you would call those water molecules and you would call those sodium chloride formula units. But sometimes it's just fine to just call them all molecules. Okay. So the formula, such as MgCl2 for an ionic compound, follows this convention. Okay, you always write the cation before the anion. Okay, so if you don't have good command of how to determine which is which, you may want to go back to the previous video, but recall that cations are formed from the metals and the anions are formed from the nonmetals. So if you're not great at uncovering what the metal is or the nonmetal, you may want to go back and read your textbook, but recall that the metals occupy the majority of the periodic table, mainly the middle to left-hand side, and the nonmetals are the right-hand side. And so note in MgCl2 that the Mg came first because that was the cation. It was the metal. Okay, it's in group 2, the column 2, the alkaline earth metals. And then the Cl came next because Cl is a nonmetal. Okay, charges are not written in a formula, and the total positive charge must equal the total negative charge. Thus, the entire ionic compound has to be neutral. Okay, so let's think about this. If magnesium is in column 2, so it has 2 valence electrons. Draw it as the Lewis dot diagram. It's going to lose those 2 to give you Mg with 2 positives or 2 plus. And then chlorine is a halogen. It's in column 7. So it's going to want to gain 1 right there to give you a chlorine with 8 electrons in its outer shell, the valence shell, and that's going to be with a negative charge. Now, if you were to add Mg2 plus a Cl, notice that the total charge is still a plus 1. You would have MgCl plus. Well, that's not what we do. We need to make sure that the entire charges balance out and that there's no ions left. And so what you'd have to do is you'd have to stick 1 more chlorine. You'd have Mg2 plus and then 1 Cl minus and then another Cl minus. Notice now that you have 2 minus charges there to balance out the 2 positive charges. Thus, that's why it's MgCl2. Okay. Now, keep in mind that the 2 is subscripted and it indicates that there are 2 chlorines attached to 1 magnesium. Here's a cool trick that I've discovered in solving a compound's formula. And so if you don't want to have to sit there and figure out how many chlorines, which are negative charge, goes with the magnesium or so on and so forth, here's a cool trick that helps you get through this. So first you need to identify the charge the ion would have. And so let's act like you're trying to mix calcium and phosphorus. Well, you know calcium is in group 2, or column 2. So it's going to take on a plus 2 charge. And phosphorus is in column 5. which means it'll take on a -3 charge. Okay, so now that we've identified that, I'm going to write it here, Ca2 plus. Sometimes you can write +2 or 2 plus. Either notation is fine. P3 minus. And sometimes you see this charge circled, which is also fine. It's just whatever you like. Okay, now what we're going to do is we're going to take these charges and we're just going to omit the actual charge sign, but just take the numerical digit. And you're going to place that right there on that side of the phosphorus, and you're going to take the phosphorus as 3 and place that right there. So what you'd get is a Ca with a 3 right here as per that arrow, and you'd have a phosphorus with a 2 right there as per that arrow. And then if necessary, you want to reduce the numbers to the lowest possible value. And so this is how you'd write out calcium phosphide, Ca3P2. And does that make sense with the charges? Well, if Ca is a 2 plus, and you know that phosphorus is a 3 minus, you can see there that it's not a neutral compound. It would be a -1 as drawn. And so just to spare you some time, calcium right here. So what we have is 2, 4, 6 in the positives and 3, 6 for the minuses. And so that's how you work that out. And then, of course, the step 3 there, if necessary, reduce down to the lowest possible value. You see that right here, because if you were to do calcium oxide, calcium forms a 2 plus charge, oxygen forms a 2 minus charge. Now, if you were to do that trick and you were to bring the 2 there and the 2 there, you would get Ca2O2. But go ahead, you can divide both of those by 2 to get CaO. And obviously that makes sense because Ca2 plus can already be balanced with O2 minus to give a neutral compound. Okay. Polyatomic ions, a difficult subject to talk about, so I want to briefly go over it. So polyatomic, poly means more than one, and so polyatomic, more than one atom. Ions, okay, so it's also an ion, and so an example of that would be the hydroxide ion, okay, it's an anion, or you might think of the ammonium cation. And so what it is this entire cluster of atoms is a unit. You never break it apart. It's not an O minus and an H plus or something like that. It's all one unit. It stays together, and that entire thing is a negative charge as drawn. And that is a cluster of atoms right there in H4. They always stay together. And so you could really think about this entire unit kind of like you do sodium, just a plus charge, except for it's a cluster of atoms rather than one single atom with a plus charge. So that's what a polyatomic ion is. But what it does is it complicates our life a little bit as we construct these formulas. And the main difference being that because you have to keep this cluster together, you're going to add parentheses to enclose it in the formula, okay? So you still do the cation first, the anion second, but the polyatomic ion must be enclosed in parentheses, okay? That's only if more than one polyatomic ion is needed, okay? So let's take a look at how. So here's some polyatomic ions you see in everyday life, actually. You just don't know it, but you don't need to memorize this table, but just know that here are some polyatomic ions. That's what they look like. And it's more than one atom together as a unit, as a cluster, and they take on a certain charge. Sometimes a +1 charge, other times a -1 charge. You see right here the phosphate is a -3 charge, okay? So always note that the charges are indicated in a superscript, and the number of atoms in a particular cluster is indicated in a subscript. So let's take the hydrogen carbonate or the bicarbonate anion. It's HCO3, so that means that there's an H, a C, and 3 oxygens, and that entire unit is a negative charge. Okay. So polyatomic ions and ionic compounds. So if you were to mix ammonium cation with a chlorine, you would say NH4 first, because that's our cation, and then that's a plus charge, and then Cl minus. You would do bring in the charges down. Trick right there to give you NH4Cl, ammonium chloride. Now again, there's no parentheses needed if it has a 1 subscript. And notice that chlorine is a 1, but you don't have to draw in 1. 1 is assumed in this case. Okay, you only need to draw a number if there is more than 1. Okay, and if you were tallying up the total atoms, you would say that this compound has 1 N, 4 H's, and 1 Cl. Okay, now let's do the same thing with this calcium hydroxide. Right here is a second example, Ca2 plus and the OH minus. We're going to bring the 2 right there, the minus 1 right there, which would give you Ca, and then OH, that entire unit, in 2 of those. Okay, I got that because that 2 got put right there. Okay. Now, in understanding how this formula works for this ionic compound, you would say it has 1 calcium and then an OH, but there's 2 of them. So actually, there's 1 of those, there's 2 of those, and 2 of those, because that entire unit is multiplied by 2. Okay. I'll do one more example for you, and then I feel like you can do the rest. Let's do this magnesium and phosphate. Okay, so magnesium is a 2 plus, and phosphate, PO4 3 minus. You're going to bring the charges down, switch them out, and then you're just going to rewrite it. Okay, so it's Mg, and then 3 from the phosphate is brought here, and then you have a PO4. You keep that unit together, and then the 2 from the magnesium goes there. So Mg3, PO4, 2, magnesium phosphate. And if you were tallying up the atoms, you would say that it has 3 Mgs, and then 2 phosphorus, and then 4 times 2, so 8 oxygens. Okay, so don't forget that subscript multiplies this entire entity by 2. Okay, so go ahead and try out the other ones and see if you can figure it out. So here's a cool slide. Again, the answers are already written in there, so just act like they're not there, okay? But it's just simply asking, can you undo a compound and tell what ions made it up, okay? So if this is kind of like a K1Br1, and you know it's written cation first, anion second, then you ought to be able to construct a K plus and Br minus to have gotten that. CaO, don't get confused. You know, calcium is not going to be a +1 because it's in column 2, an alkaline earth metal. So it's going to be a Ca plus 2 and an O 2 minus, so on and so forth. What you can do is actually deconstruct, undo the strategy I gave you earlier. So that can go there, and that can go there, and that would give you an aluminum with a 3 plus and an oxygen with a 2 minus. And you can just simply look at the valence electrons as per your periodic table to figure that one out as well. Just keep in mind that the very first atom written is the cation, and the next one would be the anion. Real quick, this ammonium dichromate right here, just undo it. So that 2 needs to go there. So you're going to have a Cr2O7 and then a 2 minus. And then the NH4 needs to be a unit together, and that's going to be a plus, because if it was more than a plus, then that dichromate would have had a parentheses around it, but as it stands, it doesn't. Okay, so it's assumed to be a 1. And recognizing ionic compounds, I've reiterated this a few times now, but I just want to say it one more time. You recognize ionic compounds because it's between a metal and a nonmetal. So if you're not skilled at identifying metal and nonmetals using the periodic table, you need to practice and get good at that as soon as you can. So compounds between a metal and nonmetal are usually ionic, and if you recognize in the formula any sort of polyatomic ion, then it's also ionic. And so if you see sodium dichromate right here, it's a nice orange crystalline powder. Well, it's really just a crystalline structure. Na2Cr2O7, it came from Na plus and Cr2O7 2 minus. That's an ionic compound because it's a metal and a polyatomic ion. Potassium permanganate, strong oxidant. That one is a K plus and an MnO4 minus. silver nitrate, Ag plus, and NO3 minus. So all of these are ionic compounds because you notice that it either has a polyatomic ion or a metal attached. So hope that made sense. Again, consult YouTube or Google for extra help, or email your instructor if you need further clarification. Have a great day.